Hello everyone, thanks for watching this video. Here I'm going to talk about our work, HART, an hardware-assisted modular tracing framework on ARM. I will introduce this work from 6 aspects: introduction, background, HART, Hudson, evaluation, and conclusion. Linux leverages the kernel module mechanism to enhance its extensibility and maintainability. Thus, the third party can design their own functions to access the kernel, such as hardware drivers. However, the vulnerabilities in the kernel modules have been a serious threat for the security of the Linux kernel due to the lack of code correctness and testing rigorousness. CVE patches to kernel drivers comprise roughly of 19% commits from 2005 to 2017. In 2017, 41% of 660 collected bugs in Android ecosystem came from kernel components, and most of which were device drivers. To solve the problem, many solutions have been proposed, and we classify them into 3 categories: memory debugger, integrity protection, and kernel isolation. The first category is to detect illegal memory access at runtime, aiming to achieve memory protection in the kernel. The second category of approaches explores to ensure the integrity of the kernel, including control flow, data flow, and code integrity. The last category of solutions isolates the modules from the core components so as to confine the potentially corrupted drivers running out of the kernel. Some representative works are listed in the right side. However, the problem is far away from solved. These solutions all need source code and require extensive modifications to the main kernel, which is intrusive. Most solutions also incur high performance overhead. These limitations will definitely affect the usage of the solution in practice. Thus, to overcome these limitations, we designed to build a high-performance tracing framework for unmodified kernel modules without module source code, that is, the HART. Before the detailed introduction to our work, we first give some background of the hardware we used, the Embedded Trace Microcell, ETM. It is a hardware component on ARM processors and is able to tracing the instruction execution and memory access with negligible overhead. A general model in the figure shows that when CPU executes instructions, ETM collects information about control flows and memory accesses. Such information can be compressed and stored into an on-chip memory called Embedded Trace Buffer, that is, ETB. It is accessible through mapped I/O or debugging interfaces. Then, we will take a look at the overview of HART. HART is designed as a standalone kernel driver. At the high level, it manages ETM and ETB to trace the execution of the target modules, and PMU to raise interrupts, and the trace decoder to parse the ETM trace. HART also hooks entrances and exits of the target modules. Next, I will introduce the design details in HART, typically the challenges we met and the corresponding solutions. The first challenge is about the selective tracing. As a hardware component, ETM is lacking of OS semantics. Since the filters in ETM is limited, it is hard to identify the trace of the target module from the output. Besides, the size of the trace buffer is limited. We need to trace the selective execution in the kernel module instead of the entire execution in the process and the other components. To achieve this goal, we hook the entrances and exits of the target module during the module's initialization by the callbacks registered by the trace point, which will not intrude to the kernel. Then we replace them with the wrappers during the relocation stage, as shown in this figure. We consider both conditions in the data and text segments. The second challenge is to achieve continuous tracing. As I have mentioned before, the size of the trace buffer ETB is limited. According to our observation, most devices are equipped with a 4K trace buffer. Thus, the buffer could be fully occupied in milliseconds or seconds. Since the trace buffer is a ring buffer, when an overflow happens in the trace buffer, the older trace data will be overridden after overflow. And finally, the overflow of the trace buffer will lead to the loss of trace. Thus, we introduce PMU to bring the timely interrupts before the overflow happened. Generally, an ARM instruction carries at most 6 bytes of trace data. Accordingly, we set 670 instructions as a threshold for the 4KB buffer and ensure an interrupt every 670 instructions. During the interrupt, we validate and extract the trace with carefully designed algorithm. The last challenge is to improve the performance. Since the ETM incurs negligible overhead, we need to pay attention to the performance of handling the trace, exactly extracting data from the trace buffer and decoding them. So, to decode the trace efficiently, HART spawns a decoding thread for the target module, and we design an elastic decoding scheme, which yields the CPU based on the workload of the decoding thread. The slower the trace grows, the longer the thread sleeps, and vice versa. In this way, HART leaves more resources for CPU while the decoding thread is not busy, but also ensures the decoder of high efficiency when it owns a heavy workload. Based on HART, we also built an address sanitizer named Hudson to demonstrate the extendability of HART. The design of Hudson reuses the scheme of address sanitizer. We set red zones for out-of-bound detection. These red zones surround the objects, and once the red zone is accessed, an alert will be raised. We only allocate shadow memory for the kernel space. Totally 130 million bytes continuous virtual space are allocated for the shadow memory, with each shadow memory bit mapping to a byte. If the module source code is available, Hudson can achieve the same level protection with Kernel. However, if the module source code is out of reach, Hudson can still achieve heap protection, while Kernel will not work at all. The reason why Hudson only focuses on heap-related memory vulnerabilities is that without source code, we cannot locate local and global arrays, which prevent us from wrapping those objects with red zones. Hudson can achieve heap protection without source code by hooking the Slabs interfaces for memory management. The interfaces Hudson currently supports are listed in 3 categories in the following table. Then we come to the evaluation. The evaluation is conducted on Freescale IMAX53 Quick Start board. For comparison, we also test under the state-of-the-art solution Hudson. Since the IMAX53 board can only support 32-bit systems, while Hudson is only available on 64-bit systems, we run the Hudson-based experiments in a Raspberry Pi 3 Plus, configured with the same computing power and memory. We collect 6 widely used modules and come with standard benchmarks. For the overhead to the main kernel, Hudson places a significant burden on the main kernel, 3.3 times on average. By contrast, HART and Hudson introduce no overhead. This well supports the advantage of our works in terms of no modification to the main kernel. For the overhead to the module, HART and Hudson barely affects the performance. On average, HART introduces an overhead of 5%, while Hudson introduces 6%. In general, the hardware-based tracing involves negligible performance overhead, and almost all the overhead introduced by HART is caused by decoding and analyzing the trace output. As to Hudson, since it cannot be deployed to the modules without Hudson-enabled kernel, to some extent, we can analyze the impacts through the differences between the tests with and without Hudson-based, with and without Hudson-enabled modules, that is, the right two columns. In the network and file system modules, these differences do not necessarily imply that Hudson is the most efficient, because most of the time is spent on I/O access, and the computation in the kernel is quite simple and quick. In the USB storage driver, most of the computation in the kernel space is performed by the target module and takes more time than I/O access. Thus, the cost of adding Hudson on the module is significant, about 2 times. In the tracing evaluation, we can find that overhead in ETB never happened, so that all the trace data has been successfully backed up and decoded. HART and Hudson have achieved continuous tracing. The differences lie across different families of the modules are also consistent with the performance evaluation. A higher frequency of backing up incurs more trace management and thus introduces higher performance overhead. In the effective evaluation, we collect 6 known memory vulnerabilities which cover different types and lie in different modules with various categories and complexities. We can see all 6 vulnerabilities are successfully detected by Hudson, which proves that Hudson has a comparable security performance to the state-of-the-art solutions. Finally, it's time to conclude. In this paper, we have following contributions. We present HART, a hardware-based high-performance tracing framework specially for kernel modules. The second one is, based on the HART, we built a modular security solution, Hudson, to effectively detect memory corruptions without requiring the source code of the module. Finally, the evaluation result shows that Hudson can achieve the detection with only 5 to 6% performance overhead, which is significantly superior to the state-of-the-art solution, Hudson. That's all. Thank you.